Hi, and welcome to another Hopper Languages video. This one is going to be on the Hopper file system. I'm going to talk about some of the design decisions I made, and I'm making this video with the eye to how you would implement a Hopper file system on an alternate platform. I've got this program called MCU Shell, which is a version of the Hopper shell that runs on RP2040 MCUs, and I'll demonstrate it in a second. If I go out to the Hopper shell and I do a dir of the root folder, you'll see here it says 4 non-Hopper compliant paths ignored. So let's talk about the constraints of the Hopper file system. Non-Hopper compliant paths, I decided that having a dot in a folder name is a bad idea. So you can only use a dot in a Hopper path for an extension, and you can only use one dot at the end of the file name. I've overconstrained the limits of the file system right now. We can always extend it later if it becomes a problem, but it's nice to start with it sort of locked down for now, and it hasn't been an issue. The non-compliant paths that are being ignored here, just out of interest, are things like dot and dot dot. The current folder and the parent folder. And also the hidden paths for the Git version control system, which you probably don't want to see in your Hopper shell anyway, because you don't want to go messing with them. Anyway, so that's what that means. It's just warning you just in case you make a mistake. And the kind of mistake you could make where you suddenly can't see your file anymore is you might put a space in a path or in a file name. And in Hopper paths, spaces are illegal because I didn't want to have all the annoyance of having to put quotes around things when you put spaces in the paths or in the folder name or in the file name. So Hopper's nice and simple in that regard, in that a space is a delimiter in a path no matter what. So it is always a delimiter between arguments. Keeps it simple. Another limit is that Hopper is an ASCII system. So the digits, the paths are limited to what's available in ASCII, and it's even more limited than that. But it means you can't have Unicode characters in the path, right? So, and that's for good reason, because we're trying to support file systems on little systems like little FS on the microcontrollers, where they do indeed have these limits. Their file system is ASCII only. Okay. Case sensitivity. Two of the major desktop platforms are case insensitive. So Windows and Mac OS are case insensitive. Even though Mac is like a Unix file system based on FreeBSD originally, it is case insensitive, its file system. You can switch it to be case sensitive, but by default it is case insensitive because it's much easier for newbies, beginners, to not have to make that mistake of wondering where the hell their file is simply because they press the shift key. The exception to this is Linux, which is always case sensitive. Anyway, in the Hopper file system, it's case insensitive. So the way I've been implementing that on the microcontrollers, for example, is I make, because little fs is case insensitive as well, but to make it more obvious, I just make the file system, make the path lowercase. It isn't like that on Windows. You can see there's some uppercase paths here, but on other file systems, the easiest way to do it is just to always lowercase anything that's being sent to the file system. Right. This is the port command, which tells me what COM ports I've got. I select COM1. It says I don't have COM1. Oh no, wrong command. This is the terminal system. Same idea. Oh, why am I not connecting? Maybe I am. Maybe I just don't have the program running it. What a fantastic demo. Oh, I can fix it this way. I think I just did fix it by restarting. So let's restart, plug it in. There we go. It's restarted, and just do terminal. There we go. I'd obviously broken into the terminal shell with Control-C or with the debugger at some point, so it wasn't running. Now it is running on my microcontroller because I restarted and it automatically launched it. So that's a good time to talk about snafus with on the RP2040. If it's automatically launching the last program you installed, like in this case, it's the MCU shell, and you can see now the feedback from the shell is in green rather than in blue because this is running on the microcontroller. Now, if for some reason you get stuck up in this and it keeps launching something that sort of bricks your microcontroller, what you can do is in the Arduino system where you're uploading your firmware for your microcontroller, you can switch this load auto to false and it won't just keep running the last thing you loaded so that you can get back into the debugger or get back into the monitor if you want to. And yeah, while we're here, if Arduino updates the firmware for your board, sometimes it resets whether your board is configured to have some of the flash used for little FS or not. So it reconfigures this to be no file system. So it's always worth checking on your tools menu that it says file, that you have a file system. And the other thing it resets, which is annoying, is the optimize setting, which I always have set to fast, and it'll set it to small by default. So yeah, good to remember those two things. Right, let's go back. So right now we're running little FS. We can do a dir command. You can say help here, and you'll see what file system commands I've ported to the microcontroller. So, we can say cd bin, for example, and then we can go bin like that. So we've got our little, and we don't need to do this because of path, so we can cd dot dot, and we've got a Mandelbrot here. Or we've got Tigger Basic. So the console there changed from a slash to just like that, and there's another dir command in here, which is the basic dir command, and I can say load Knowles RetroLab benchmark, and I can run that. It says it ran in 0.1 seconds, but the answer for the benchmark is only 10,000, which means it was running in 16-bit integers. Whereas if I exit out of here, by rather than exit for basic, and I run, so if we go dir bin, there's a hexy version of Knowles RetroLab as well, which is the Hopper version. So if I run the Hopper version, it's got a much bigger answer. It runs 4 times as slow, but it's using 32-bit longs instead, so it's doing a lot more work. Speed, I haven't used this for a while. We can overclock it. And then we can do Knowles RetroLab again. And suddenly we're running twice as fast, so 200 milliseconds anyway. So yeah, you can overclock your Raspberry Pi Pico. So I'm going to, while I'm thinking about it, set it back to, it'll set back when it reboots as well. This is the Hopper commands to overclock. All right. Let's exit from, we don't actually have to exit, but I'm going to exit out of there. And I'm going to exit from the terminal. And now I'm going to show you how you do this. So inside the MCU shell folder under projects, there's an ms.cmd, which is a Hopper console script to build the system. And what it does is it rebuilds all these console commands with a command line define for serial console. And that makes them all work with the serial console rather than with the GUI console, which is, the GUI console is like the screen and keyboard units, whereas the serial console is, the serial unit plus the I/O unit. So it builds all of these, and it builds all the samples. It builds some utilities like mount and eject, which is for mounting an SD card. I don't have one connected to this device right now, but it mounts the SD card always in a root folder called /sd/, and then all the files on your SD card just magically appear in the regular file system, which is in the RP2040 flash, is where the regular file system is. They just appear there mounted in a subfolder. Once it's built them all and all the samples, it uploads them using the Hopper monitor and the -t, which is to transfer files to a Hopper monitor. So from the local path to putting them in a folder on the Hopper file system on the microcontroller. And then once you've uploaded everything, it's kind of important to rebuild all those shell commands for the Windows system. Otherwise, your shell commands won't work because they'll try and use the serial port version on Windows where they shouldn't. Anyway, by having a RP2040 type system plugged into your system and having the firmware already on it, you just run this script and you'll get this whole demo set up for you. I highly recommend you don't do this first, and that you go and do a simple blink example first, because it's quite annoying if the script fails a long way down the script. Okay, let's go back and have a look at the file system now. Right, more about the file system. Under system, there's two units. There's file and directory. Here's the file system. Let's start by talking about the file system. There's also the path. Let's have a look. Actually, let's look at the path. Path is a set of utilities for manipulating the path, and they're all written in Hopper. There's no system stuff here. It's all just Hopper string manipulation, so that if you want to combine two parts of a path into one, like a folder and a file, it'll glue together the path with the path delimiter. And it won't put extra ones in, and you can and there's things like get me the full path for a relative path, all those sorts of get extension, get the full path, all that sort of thing. And these utilities are the same as the ones in the .NET framework in terms of their behavior, very, very similar, except for valid path character, which I was talking about earlier. It's got to be a letter or a digit, or it's got to be a dot or a slash. And so these are if you're familiar with how the .NET framework path type works, this is very similar, and that was similar to what was in Java, because that's mimicking what was in Java. Similarly, the file and directory APIs were also based on the .NET framework and C#. So the exists and delete and all that, and read a line. So they're very, very similar, except that I added something else. Right. So why did I do it this way? There's some APIs here have been written in source code, and we'll have a look at one of them in a second, so that I can walk through how the file system works. But an interesting thing to note right now is that some of the file system APIs take a file argument, and it's usually named this, because you can use the shortcut to put it in front of the like you would for an object. There aren't objects in Hopper, but this is syntax shortcut, a syntax sugar for. I'll show you in a second how that works. But the key is that some of the APIs have this as an argument, and some of them have a string argument for the file that you're passing in. So you're either passing in the file as a file object, or you're passing the file in as a string. Now, what's the difference? The ones that take the path as a string are atomic. In other words, they do everything you wanted to do with that API in one shot. So if you're asking if a file exists, come back, you're done with it. You're asking to delete a file, you delete it, it's done, right? You get the time, you get the size of the file, you're done, right? Whereas, and the exception to that is open and create, where they actually return you you see, these return you a bool or a long or nothing at all, or, get the date and time, returns you a string. But open and create return you a file handle, so a file object, right? And then you can continue to do more things with that file object once it's been created. And that's how the file system works. And then you've got a utility method called valid to tell you whether your file is good or not. Why do I have valid? Why don't I just return a value, right? Well, if you go and look at the numeric types, if we look at uint, I've got this try pass method. And that's because I really don't like APIs that use the return value to also be an error message. And the classic example of that in C. So C gave us a lot of good things, in terms of a language that was better than what existed at the time. But one of the things in the design that is pretty awful is returning error values as a regular return value. And the example of one of the most awful is the C API A to I. In other words, converting a pointer to chars into an integer. Because if A to I if you have a string of characters that ends in a character that starts with digits and then ends in a character that's not a digit, like 0, 1, 2, 3, comma, something or other, it'll actually parse that and return the integer value. It won't tell you there was an error. It won't tell you it hit an invalid character. If it hits an invalid character without being able to parse an integer, then it returns 0. It still doesn't return an error. So it's a pretty terrible API. Whereas the .NET Framework way of doing it with a try parse, this method returns two values. It returns a Boolean value to tell you whether it succeeded or not, true or false. And then it has a reference argument for the value that gets returned. So this pattern is a far better way of returning two values, an error value or an actual legitimate result from your API. So I could have done this with the file system. I could have made every file API be like a try parse type API. But it would have made file operations very wordy and very verbose. So what was my solution to that? There's another motivation behind this too. If you've worked to any length in .NET in C#, then you will have found that at some point you're going to have to use external APIs that are not part of the .NET framework, that are not part of the whole managed system. And the classic example of that is calling the file system. So suppose where .NET wraps the native file system underneath everything, right? So you open a file in .NET and you start reading from it, and you read a little bit at a time. And as you're reading from the file system, someone pulls the USB stick out of the slot, and the next time you try and read from it, you fail, right? So your read operation is going to fail because someone pulled the rug from underneath you. They pulled out your physical file system while you were reading, and .NET has to fail catastrophically for that, and the way they deal with it is they throw an exception. So you have to have a try-catch around your file operations so that you can catch the exception. And Hopper doesn't have exceptions. It has, error return values. So that wasn't going to work for this either. And I really wanted to make a system that can never fail in that way. It can never fail catastrophically. So your system never crashes because the user did something. You can crash because the programmer wrote some rubbish, but the user should never experience a crash because something that's outside the control of the managed system. In other words, it can't manage it the same way it manages memory on the garbage collector. It can't stop you from pulling out the SD card in the middle of reading it. How do you deal with that, right? So my solution was isValid. So let me show you how that works. So there's an API here, which is in the sort of try-parse way of doing things, where it returns a Boolean to say you succeeded, and you pass in a string, and it's going to return a reference, which is a string, which is all the text in that file. So let's walk through how it works. Because internally it uses the isValid paradigm. So the first thing it tries to do is open that path to create a file object. And then you can check on that file object, and here you can see this syntax. So instead of passing it as an argument, because isValid takes this argument, you can put it instead of the word file in front. So you could have written this as, bool valid equals file isValid tf, like that. So that would have been the same as this, but this is syntax sugar, this argument here, for being able to write your code like this, which looks a little bit neater. And it works for all the types. It works for strings, works for everything. Right. So you try and open your file, and you check the file handle afterwards to check that it's valid. So if it successfully opened the file handle will be valid. Now you run into an endless loop, an infinite loop here, where you start by reading a character from the file, and if it was valid, then it'll come past this and it'll append it to your string. If it wasn't valid, it'll break. So the way this API works, is that it's not quite perfect, because if the file didn't exist, if there was a failure trying to open the file, it looks like it's not quite perfect, but it actually is. I'll work through that in a second. So if you fail to open the file, you get a false from there. So it looks like if you fail to read, like if someone pulled the card on you here, right, you're still going to get the true result, but you're only going to have half your content. Well, that's not really true. And why is that? It's because I know how the file system's implemented. Internally, the file system, when you open a file, reads the entire file into an internal string buffer. And I'm taking this approach because I'm assuming that we're not going to read really large files. So if you're on a 64K only platform and you try and read a big file that's bigger than 64K, you're going to have a little bit of a problem with this, making it, because it uses the string type internally for the file buffer. But on the microcontroller, where I'm only loading up programs that are like only a few K or so, it doesn't matter if I've got a string that's a few K, right? Makes it much easier to make this thing rock solid, because the only interaction with the file system in this API is during this call here. So it is just as atomic as delete or exists. So it loads up the entire file into the buffer, and then what this thing is doing is buffering and reading it in the buffer. And here again, what is this doing here, where it's saying after the last character, when you try to read beyond the end of the buffer, it became invalid. And that is again because I don't like overloading a return value. No, the last character in the file is not EOF. It's not end of file, because not all files have an end of file character in the end of the file. You can, it's an ASCII character, but the vast majority nowadays do not. So it's just a special case where if you read beyond the end of the file, you get an end of file character. Well, let's not do that. Let's just have real characters coming out of our file and check that we're still okay and we got a real character, because if you, I think it returns a 0. It doesn't return an end of file. It returns a 0, which is actually a valid car character inside a string in Hopper is 0. So you got to check the valid to see if what you actually got, if you read beyond the end of the file or not, and then you finish and you exit out of there. So an example of what I'm talking about is a 16-bit CRC value being calculated on a file. Because again, here now you're reading bytes out of the file, and 0 is a legitimate character here, and so is EOF. Is a legitimate character here, the ASCII for EOF. So how do you know when you've actually got to the end of, how do you know when that character wasn't actually an EOF character and it was actually the end of the file? Well, far more consistent if you just check valid every time after you read from the file. And this again reads the whole file into the buffer. Right, that's reading a file. So it does everything, all the file IO system stuff happens in file open. And then all the rest can be written in our own native code, which means that the only file API stuff, if we're building a second file system, needs to happen in this one API. It makes, you don't need to add it all to the read byte, read line, all these other APIs. So all these other APIs that use the file object, read. So this reads like an array of bytes, read line. You don't have to worry about them. We can implement those all in the Hopper system. You only have to, if you're implementing a file system, you only need to implement open. If you're writing a file, you need to implement 2 APIs because it's very similar. Actually, you only have to implement 1 API. The create API doesn't actually create a file. I think it depends on the file system, but it doesn't have to. It just creates a buffer. And then your append just appends to the buffer, and then all the action happens in flush. So this will create the file and write the whole file out from the buffer. So you could theoretically implement the entire file system with 2 APIs, open and flush. And inside the file object, it keeps track of whether it is you can only read or write a file at the same time. So even though there's one object for both, if you try and read to a file that you created with create, or you try and write to a file that you created with open, it'll immediately flip to invalid inside the file object. It'll immediately fail. So yes, you need to implement these the atomic file APIs as well. But for reading and writing, you only need to implement 2. You need to implement open and flush. And I think it is legit to do some file ops in the create, because you might try to create a file that's got the same name as one that already exists. I think it just overwrites it, and if you want to do that, you want to delete it first. And yeah, so you might, depending on your file system, might want to do some stuff in create, but most of what you do is in flush. And examples of the implementation where I've sat on top of an existing file system that I didn't have a whole lot of control of how it worked, would be, again, in the Raspberry Pi Pico. I implemented all these file APIs and the SD card APIs, but the file APIs are the more interesting ones, and I implemented them for LittleFS. Actually, I've got multiple implementations. So for the Teensy, there's a stub implementation, and then for LittleFS on the RP2040 devices, so valid path, finding out if it's an SD path. So an SD path is one that is in the subfolder SD, starts with SD like that. And then the implementations exists, for example. So I'm taking a path, converting it from a hopper string into a C string buffer. There's a limit to the path, but path length, but that's given to us as a constraint of the LittleFS system anyway, that you can only have a path up to 32 characters. And then it's calling exists and open for read. So even though it's just doing exists, it actually has to do a little more work here. And the reason it has to open it for read is because exists will tell you if it's a directory exists or a file exists. So you have to open it and then check, that it both exists and it's not a directory. And then it's the same for directory exists. You have to do the opposite. And then with the LittleFS, you don't have to close. Yeah. Anyway, remove is like delete. Write all bytes. So I've got some comments about, and these comments are kind of handy because LittleFS is actually a very C-style file system. So the things you're used to dealing with and implementing in a C-style file system, you'll see sample code here of how you would do it, how you would get from hopper paths and hopper conventions to the C-style conventions to write it out. And as you can see, it's just it's looping through and writing out a whole buffer here. So somewhere there's a buffer. The content, it's looping through the content, which in the case of hopper is just it's another string. So the path is a string and the content is a string, because a hopper string can have all the legitimate binary characters in it because it's not zero terminated, and it's got no constraints on its length. So unlike Pascal, you're not limited to a 256 byte string. It's got the length in a hopper string is 16-bit value. Very good. So I think that is a good summary of the motivations behind the limitations of the file paths, like why I did them the way I did, and why I went with is valid rather than, it got over two problems. It meant that unlike if open in C, I don't return a null as a failed file open, because there is no such thing as a null pointer in Hopper. It can't be done. There is no null for an object. And by not having null for an object in Hopper, you avoid an enormous amount of potential errors. So an object either exists in the garbage collector or it doesn't. Period. So when you create a new string in Hopper and you go string, my string, that is not a null pointer. That is a new empty string. Everything is zero initialized, and in the case of a string, that's an empty string, right? So there's no such thing as a null pointer. Having said that, I lied. The one exception where there is a null pointer is a delegate. So a delegate is a pointer to a function in Hopper, and you can have an uninitialized function, a function pointer. So you can create a delegate, a delegate pointer to a function that's not initialized yet. But if you try and call it, you will get a failure. It won't just crash. It'll give you it'll fail with a die crash, but you'll see it at the developer will see it at the time that they're developing the program. It won't be something unexpected that happens to a user because you try to open a file that doesn't exist, that the developer couldn't have anticipated. In the case of trying to open a file that doesn't exist, when you try and call it with open, immediately afterwards it's not going to be valid. Now, interestingly enough, if you do try and call any of the file APIs on an invalid handle, they never fail. They just return zeros. So, and so you'll just get 0 returns. They won't fail. They won't crash. But you'll get bad data from them if you don't check valid on them. But they never crash. So there you go. It's a managed system that doesn't crash even if the external thing we're wrapping fails. That's the idea. Okay. Yeah, I think that's... Trying to think if there's anything else I haven't mentioned here about how we would build another file system on this. No, I think we're good. But if you think I've missed something, you should add something in the comments on this thread, on this video, because then I'll reply to the comments so that other people can see it as well. Very good. Thank you for watching. And I'll link to the Hopper Languages playlist, since this is sort of platform independent, Hopper language specific video, or Hopper runtime specific video here, rather than any specific platform. Cheers.